All right, let's see if we can get this thing rolling today. A few minutes later, source searches. Let's go. Well, that's been okay. Let's see. Let's make that first homework due on Tuesday. I think you should have had enough time by then to get it done. Okay. Let's see. I wanted to make a few more comments out of the carrier program. This is the one I'm open. Also, please consider going to ASHRAE Student Night if you haven't. If you intend to go, it'd be nice if you let us know. Certainly, if you want to ride the van, you need to let us know so we don't oversubscribe the van. But please consider going. That's a great opportunity for you. I know sometimes when you haven't been to these things, it's hard to appreciate, what people are doing for you. But they really do want you to attend. Okay, let's see. I don't think we've done much on creating plants and that sort of thing. So I showed a little bit of that last time, but you can, I guess there's two ways. You can build the chiller cooling tower and then just call it up from the plant, or you can go from the plant and then there's an opportunity to build them from the plant out. It doesn't really matter. Let's just say we wanted to do a chiller here. Let's do a new chiller. Your next assignment is going to be to build some absorption chillers and compare those. Okay. And so I'll just give you a little preview of that. So we'll call this single stage. Okay. And then equipment function. So you can look down here. So that would be reversible, would be kind of like a heat pump for heating and cooling, or a heat pump to produce hot water only. And if you have questions on those system types, you can hit the F1 key and get all that information. I haven't read up on that stuff recently. But so this would be just for a chiller. And then once you tell it that, then it's got a whole bunch of different chillers here. Let's see. So single effect absorption. Pretty simple. Select the one that you want. Bingo. Okay. You can put notes if the data source or something, but usually just leave those blank. Okay, so here would be the design inputs. I think in that homework, I tell you to run 42-degree water just to make you change it, So, it's pretty simple. This is leaving chill water temperature, full load, entering, that would be, that's condenser water temperature. What CWT. Okay. And so if we wanted 42, we just put 42 in there. Here are the flow rates. This is what it's defaulting to. So the carrier program defaults to 2.4 GPM per ton. That's on the cooling side. That's the evaporator flow. That's the chill water. I haven't told you to change that, so as far as homework's concerned, there's no need to. But notice, look at the condenser. This is the cooling water flow. It defaults to 3.75 GPM per ton. Well, for our centrifugal machine, it's going to default to 3 GPM per ton. And so when you do these absorption, you have to note that, because when you define a cooling tower, you have to make sure that you get the flow rate right between your chiller. You know, you tell it the cooling tower is rated for this flow and the chiller is rated for a different flow. I'm not sure if that gives you an error or just a bad simulation, you know, but you want to try to not do that. So you don't have to change this. You just have to remember it so that when you define your cooling tower, you can, you know, get them both set to the same flow. Okay. There's some controls and stuff in here. You can auto size. Let's see. This shows the steam input, and that's what it's defaulting to, like efficiency wise. You know what, in the slides, I'm not sure I can remember. It seemed like it was like 18 or something. But again, I haven't told you to change it, but you know, that's the required steam flow. So that's input power. Average operating loss, and for the electric input, and see, it's defaulting to 6 kW. Okay, and that's for pumps and stuff like that. And then steam energy content, that's the BTUs per pound based on, I'd have to go back and look in the steam table, see exactly what pressure that is. Not sure off the top of my head. But anyway, those are the input screens there. And then performance. It has this performance map, and they have gotten this from, this is Carrier, so I'm sure this is from some Carrier chiller. But if you had detailed performance information on a particular unit, you can input your own. And so this is based on the entering condenser water temperature and then the capacity, and that's the, at max capacity, that's the pounds of steam. That's this number over here. Well, that's pounds per ton hour. Say, so that's kind of how this thing gets modeled. It goes through, the program goes through and calculates a load, and then it calculates a percent load on the chiller, and it says, okay, for that hour, in order to produce that amount of cooling, I had to use this amount of steam. So all that. And then I don't know, this is, I guess these are, I've never dug into this. I've not changed it. Performance factors and how things change with degrees and all that sort of thing. So anyway, you can accept that. So you say, okay, and we've just defined a chiller. So it's not very hard. Now, to do that, to run a cooling tower with that, which I need, I'm going to define a new cooling tower here. And I'll call this the, I'll just put 1 stage absorption tower. Okay, so because I'll have to select this when I define the plant, and I'll make sure I get the right one. Okay, so it's just a cooling tower. These are the design parameters, and we'll be talking a lot about this going forward. It's got some default numbers on kW per ton for the fan load. Okay, so here, say here's GPM per ton. It's going to default to 3, so this is where I want to put 3.75, and then I'll have that in there. Your base model, you want to do fan cycling, but as an option, one of the things you'll investigate are some of these other types of control on the cooling tower fan. Fan efficiency, I probably should put that in there. I guess it's not going to let me put that in there. So it's grayed out. I don't have to worry about it, do I? Okay, so that's saved away. And then I go to plant. And then, let's see, I don't have an absorption. Okay, so I'm going to define a new plant. I'll call this 1 stage absorption plant. And so tell it what type of plant it is. So it's a chiller plant. Okay. And systems. Now this is where I'm going to tell it what air handling systems within the building are served by that chiller. I mean, if you had a big building, I mean, it's probably not going to be sequestered off, but you know, it could be, you know, whatever. So it's fairly flexible. So you can click and then shift click, I think, get them all. So I'm going to put those in Domestic hot water, that's not the kind of plant it is. Configuration, okay, so equipment sizing. You can specify particular equipment. I mean, I could say, I'm going to put it, I've got an old 1,000-ton chiller out there in the barn, and I'm going to put it in here. That may turn out to be a 400-ton load, but what the heck, I can put a 1,000-ton chiller in there. Probably not a good idea, but you know, the software will let you do it. So I'm going to let it auto size, and I'm going to say there's just one. You can put in multiple chillers, and you can put in oversizing capacities. If you have multiple chillers, how are you going to share the load between the chillers? I mean, it gets fairly detailed. Design leaving chill water temperature on this one. I'm going to try to remember. You know, it's really kind of ugly to make you change because you got two places you got to change that 44 to 42, and it's real easy to forget to do that. Not that it probably makes the tremendous. Okay, free cooling. We're going to talk about that today, but we're not in there. And 1 tower per air-cooled chiller, because right now I just have 1 and 1, so that's fine. Okay, so say here's the chiller, so it doesn't have one, so it wants me to pull down and select one. So those are the ones that I have already defined. If I needed to, I could click this and it takes me to the chiller definition page right there, but that, you know, I went ahead and did it. So I'm going to put the single stage absorption, auto size. See, it sees the 2.4 GPM per ton on the evaporator and the 3.75 GPM per ton on the cooling tower, and I don't have a cooling tower, but I need one. So I'll put my 1-stage absorption tower and say it's good. It's good if these two numbers match. Okay, and that's all you have to do there. Distribution, these are your pumps. Chill water pump, and somebody said we were using what, 70? Whatever. I should, in the assignment, there should be a feet of head on the pump. If you don't put anything in there, you won't get any pump energy, you know, because you're sounding a pump. It doesn't take any input energy to produce 0 feet of head. You know, feet of head is just pressure. You know, for standard water, there's what, 1 psi is 2.31 feet of head. So, you know, when it says, you know, I mean, you could, I don't know if you can change units on it or not. You might be able to, but pump jargon, we usually talk in feet of head. So I'll put 70 in there and have a number. And the efficiency of the pump itself, and then the efficiency of the electric motor that's driving the pump. What are we pushing? Fresh water, standard density, standard specific heat, all that. And then on the condenser water side, let's see, constant, you know, there's different ways to control it. I could have variable speed, variable flow, but we haven't gotten into that. So this is, let's see, I'd rather give feet of, yeah, I'm going to give feet of head. There's different ways to put the pump energy in, but I'll just stick 80 in here. I don't know. And then again, a pump efficiency and a motor efficiency. Okay. So if I say, okay, oh, I got to give it a steam source. Okay. It wants a steam source. Okay. So it has to have, you know, for absorption, it has to have heat, right? So this is set up right now. I think you can also run a hot water boiler in it. Seems like when I've run this before, I think that's why that hot water boiler's here. But let's just, you can say you have a remote steam source, which means you're buying it from somebody. You got a pipe coming across the fence that's giving you steam. All right, so it took it. So then in my building, I just go back, and so I can take out my scroll chiller and I can put in this. Systems, all the same, miscellaneous, and meters. It's probably going to want a remote steam cost. So I'm going to just test cost, therm, that's fuel rate. Say 50 cents a therm tax. See what happens here. Remote steam. Okay, well, let's see. It might run. You never know. Might get an error here. I don't know. Detailed use profile. Okay, so if you want the detailed information on the electric bill, then and this is what it sticks at the very end of the reports. You can also ask for it on. Let's see what it says on remote steam. It'll probably blow up. Yeah, it's gonna run. There we go. So I got a report. Seemed like my cost before was 233,000, something like that. So this is 261 with a single stage absorber. And I'm not saying this is very good. I would, if I was going to do it like to compare to your homeworks, I will go back through here a little more carefully and make sure I'm getting all this stuff right. But anyway, give you some idea how to make this stuff happen. Let's look at this remote steam and see what we get down here on the bill. Electric. Well, where's my steam? Electric. Use by month to get therms. I don't know. It's kind of like it didn't. Did it do what I asked it to do? Remote steam. Oh, I see. I didn't click anything here. This is the one. I changed the wrong one. Operator error. It happens. All right, so let's see what we get down here. Well, it's trying to give some details, but anyway, you get the overall out here. We might get some more. Yeah, here's some more detail on remote steam. So I don't know. You can look at that. It's a little bit of a breakdown. But, and then I would, again, I would save, when you get them right, I would save each one of these individually. And then you can go back and open those files and pull the numbers out to put in your Excel sheet to actually do the comparison. Unfortunately, it would be nice if the software would let you, say, run a base case and then make a modification and do all of that subtraction, let you see the differences, but it's not set up for that. So we can't do it that way. Okay, questions on the carrier program? I think between I think there's a couple of videos posted and what we've done in class. Hopefully you're coming along on being able to operate it. So, all right. I guess I'll save this away. Okay, so, oh, I know what I want to do. Just pass these around. This is a good old psych chart. So we need to, I want you to have one of these. Probably should pull up one of those. See if I can find some psych charts here. There we go. So we're not going to do much today with this. We spent a lot of time. The first course we spent probably 2 to 3 weeks just doing psychometrics. But we're going to be talking about wet bulb temperatures and approaches and that sort of thing on cooling towers. So I thought I would put this up here just for a minute. dry bulb temperatures down here on the bottom. This is a standard sea level chart. Atmospheric pressure, one atmosphere, 1.031 something 25 bars, or 14.696 psi is what it says for units. This is the good old imperial unit chart, which I claim to. Yeah. And so we go from, this one goes from 32 up to 120 Fahrenheit. So these are dry bulb and they're coming vertically. These are different relative humidity lines sweeping across from 10% to saturation. So this is 100% saturation on the air. And so at saturation, dry bulb and wet bulb are the same. Okay, so that's the way I always find my wet bulb temperature, is I come up here on the saturation curve like 60, and this line that comes kind of slant out of here, that's a line of constant wet bulb all the way down to here. Okay, at 65. The dark one is enthalpy. So we got an enthalpy scale out here. And the wet bulb and enthalpy lines are not quite parallel. I guess the enthalpy lines look like they're a little bit steeper, because the wet bulb is the not the voltage, just the curve that doesn't stand out quite as much down through here. But anyway, so when we talk about a tower, we talk about an approach temperature. And the approach is how closely we can get the leaving water temperature to the wet bulb temperature. Because say when you're cooling something with evaporative cooling, the lowest theoretical temperature you could ever get to is the wet bulb, because you're evaporating, and the more you evaporate, you take energy away, and that lowers the temperature of the flow. But when you get to the wet bulb, when you get to saturation, the dry bulb and the wet bulb are the same, and you have no more ability to evaporate. So the wet bulb is like the lowest, the best you could do. So for a given load, a given amount of heat that you want to reject, in order to get closer to the wet bulb temperature, you have to make the tower bigger and bigger and bigger and bigger. You know, bigger, spread the water out more that's fallen down, bigger will evaporate more water, which gets you colder. And so the infinite tower would produce the wet bulb temperature with maximum evaporation. And so the approach there would be zero. You can always think about an infinite tower has zero approach, because the water leaving the tower is the wet bulb temperature. That's how you can sometimes remember what approach is on a tower. So, and I've got presentations, we'll go over this, but just, you know, a little bit of a coaching talk on the front end. So, you know, in general, this is the moisture scale. This is going to be, you know, quantity of moisture per unit mass of dry air. So down here on the very bottom of this, that very bottom line, the x-axis, where we have dry bulb temperature indicated, is the only dry air on here. As we come vertically, as we rise vertically, we're adding more and more and more moisture to a pound of dry air. Okay, and that's what, in US units, that's what this unit is. It's humidity ratio, and it's pounds of water vapor or moisture per pound of dry air. So all the way up here, you know, you can get the highest, what is it, about 0.03, so 6, yeah, about 0.03 is up here at the very top. So 0.03 pounds of moisture per pound of dry air is a boatload of moisture. May not sound like a lot, but it is. Okay. And, you know, it's also interesting at that point, look at, this is the 40% relative humidity line. It goes right about through that point. So at 120 degrees, that maximum moisture is only 40% of what air could hold at 120 degrees. So as we increase this temperature, the amount of moisture that air can hold goes up. I mean, it's like some sort of a parabolic curve, a mild exponential or something. Anyway, it goes up significantly. If I've got cold air over here, if I've got air at 32, if I come across about 0.004 is all it can hold at 100% saturation. So you have to have an appreciation for how much moisture the air can hold as a function of its dry bulb temperature. Okay. All right. So you've got those, file those away. We'll pull them out and make reference to them from time to time. All right, so let's jump into cooling tower stuff. Oh yeah, and I've stuck one more slide. You don't have this slide. I keep sticking stuff in on you. But I want to define one more thing. All right, so we've talked about an air side economizer. That's on an air handler where we open up some dampers and we just blow cool air into the space to accomplish air conditioning. So that's air side. This is what's called a water side economizer. And so if it's cool enough outside, I can generate my chill water temperature with condenser water by just running the fan on the cooling tower. Well, then I can turn off that 500 to 1,000 horsepower motor in that chiller, and I can run maybe 100, 120 horsepower of cooling tower fans, and I can save a boatload of money. So that's worth looking into. Now, to make it happen, I have to buy a little bit of additional hardware, okay, some valves, some controls. The way it's usually done is to buy a plate and frame heat exchanger. So if it's cold outside, let's say it's 35 outside, 30, 35. Well, the big buildings on campus may still need some air conditioning. They still run chiller all through the year. Okay, now they don't need as much because all the spaces on the outside of the building need heat, but the core spaces in a big building, they need cooling all the time they're occupied because you got lights on, you got people on, and they're all surrounded by conditioned space. They don't ever know what temperature it is outside. Like my office, except for all the air leaking down the hall, my office would never know what temperature it was outside because I'm conditioned above, below, and all the way around if that conditioning works. I'm in there with my little refrigerator and my computers and, whatever going on. It's all lights. It's all generating heat. I should not really need to heat that space. And in fact, even when it's cold outside, I should have to air condition. Okay. So that's why we have to have this air conditioning. So, if it's cold enough, we turn off the chillers here and we say, we don't need you guys. Take a week off. It's cold outside. So what we do is, we bring our condenser water back, which is pretty warm, dump it in the top of the tower. The fans run as needed, and say we have 40 degrees. We can cool it to 40 degrees right here. So we pump it out, and we pump it. We pump it out, and we would pump it into this heat exchanger, one side of the heat exchanger. And so it would come in at 40 or so and come out maybe at 55 or 60 and go right back. And they're showing this going through the chillers. It would be better to have a bypass so you didn't have to incur that pressure drop through the condenser. But the chiller's off whether you're having to pump through the condenser or not. And then, you come out of the condenser, you go right back to the tower. So this is the only thing operating, and this heat exchanger. And then these pumps are circulating. So it's pulling water. So you shut this valve to force the flow through the heat exchanger. So it comes in warm. Again, maybe 52, 53, 54. It comes out maybe 45, 44. It's pumped up. Just goes right back out here and goes right back to the air handlers that are doing the air conditioning. So I just want to make you appreciative that we have air side economizers and we have water side economizers. And I'll have some handouts for you on this, but because this gets referenced in this presentation shortly, and I thought, well, I'll at least give you a primer on what a waterside economizer is before I start making reference to it. Okay, let me jump up to the top of this. Now, this is a presentation I have handed out. Let's go up to the top of it here. Here we go. My old buddy Bill Turpish, Shelby, North Carolina. He's a character. He is a character. Okay, so these are his slides I have shamelessly stolen. Okay, so we're going to talk, just kind of get the jargon down and all those sorts of things. So one type of cooling tower is called forced draft, which means you're blowing through the tower. So we have fans down here, someplace, sometimes they're on the side, sometimes they're underneath it, whatever, but it's pulling air from around the base of the tower and blowing it up through the tower, forced draft. Okay, we can have induced draft, and we're going to say that on the induced draft, we can have cross flow and we'll have counter flow here in a minute. So the induced draft, the fan is up here. It's almost always a propeller fan. It can either, and the motor will be up in there too, and it can be belt driven or it can have a gearbox. The gearboxes have lots of maintenance issues. TVA, the Magnolia power plant, has this kind of thing with gearboxes, and they're wanting to get rid of those dang gearboxes like crazy because it's like 100,000. I mean, of course, theirs are big. They're 200, 300 horsepower fans. Everything's big at a power plant. And it's, I don't know, $50,000, $100,000 to rebuild a gearbox. And they've got, they've got 5 cells per tower, 5 fans per tower, and they got 3 towers. So they got 15 of these things. So they do 1 to 2 at least a year at the tune of probably $250,000. So they would really like to get rid of these gearboxes. But anyway, so these things are blowing up here, and so they typically induce air on 2 sides. So the air would be coming in here, and in cross flow, so the water gets piped in the top. It's going to fall down, and the air is going to blow across it, and then turn and be blown up the top of the tower. Okay, this is a good picture here. You can see a lot of times there's slats. The air gets pulled in, and it kind of comes in at a little bit of a downward trajectory, goes across, and then bam, comes up the top of this. Some things we'll be talking more about are interference. If you have, let's say you're going to have 4 or 5 of these things in a row, this air coming out of here is basically saturated. Okay, you don't want to have this recirculated. I call it recirculation or interference or that sort of thing. You don't want this to be able to recirculate and come right back in because the purpose of that air is to evaporate. If I put saturated air in, it kind of can't evaporate, you know. So I want that ambient air coming in this thing. And so when you have a bunch of cooling towers, you're concerned about what direction does the wind blow, and is there a building over here that's going to hit, and that moisture is going to hang around and get pulled back up into the tower next door. Then that tower is not going to work very well. So there's lots of design issues. And I've got a big Marley handout that I'll give you that discusses all of that. Okay, well that's pretty good for that. Okay, this would be induced draft, counterflow, or natural draft. Okay, so the environmentalists use this picture like crazy, right? They put that on something and they put a big red circle with the hashtag in there indicating that this is a polluting source. Well, what is that coming out of the top of that tower? Water vapor. Oh, that's environmentally friendly, isn't it? Water vapor. Come on, man. Now, maybe the reactor, okay, you can put the reactor picture, put the boiler picture. But don't pick on the poor cooling tower. It's not polluting anything, you know. But it's funny how things become symbols of things. So anyway, and so this is a parabolic shape. So what's not actually, this is a very green device because these things are big and shaped like this because they usually don't have fans, and so they don't consume any electricity. And so the air inside here is warm and moist. The air outside here is cooler and more dense. And so that makes this air rise, and then the heavier, denser air forces its weight in the bottom, and it promotes a flow. And so that's the flow that goes across the fill that evaporates the water, that rejects the heat, that lets the power plant run, you know? But anyway, these poor guys get a bad rap sometimes. I need to go find a bunch of those images and stick them in there just for fun. Okay, so this again is induced. So the fan is up here. It's counterflow. So counterflow means that the air comes in around the base of the tower, turns vertical, and then goes through the fill. So the water's falling down, and the airflow is going up in counterflow instead of crossflow, where the water falls down and the air comes across it. So just fundamental different ways these things get designed. They have different operational characteristics, potentially different efficiencies, require more or less fan horsepower or kW to make them run. So we just want to learn more about them. There's some more natural draft. Those aren't parabolic. They may be parabolic on the inside. I don't know. Those look kind of trapezoidal. Okay. I was with Bill when he took these pictures. This was in Samara, Russia. And we had never seen anything like this. So, you know, this is a big, tall cooling tower. And so the intent was to take the water up here to the top, let it fall down and pull the air in the sides. But something must have gone wrong. You know, when they speak Russian and you speak English, sometimes it's hard to get all of the details in the story. But look, they had built these spray nozzles, this matrix of spray nozzles, and this is where they were putting water into the tower. So they're running fans to pull air in with this, but they're just spraying the water out down here at the ground. I've never, you know, Bill had never seen, I'd never seen that. I mean, I was doing pumps on this thing. We were there for a week. You can see that's August 8 of 05. Oh my goodness. So I don't know. He was doing cooling tower, so I didn't get involved too much with it. But that was pretty amazing. I don't know that you'll see this anyplace else. This may be a one of a kind. I don't know. That is probably going on someplace else. But anyway, that's not really how we design them. Is to just spray the water in the side and let it fall down in the basin, and you get, you know, you spray it out there, and you run a fan or so, and you got some air around, you get some evaporation, so you get a little bit of cooling, but that thing's not operating very well. And there's pictures where some sides of this thing were kind of collapsed and things were falling down, and you know, you don't want to get too close, something might fall on your head. All right. So anyway, this is more induced draft. This shows, you know, kind of a cross section of what we're talking about. You know, again, induced draft fans at the top. So we got our louvers and all that stuff that comes in. But the fill's up here. So the idea is that the air is going to go vertically through the fill as the water comes in. And on the cross flow, it's just kind of the air is flowing across the fill before it turns to the outside. Some typical design numbers. Now, you know, this presentation is probably 10, 15 years old. So some of this, like I said, is changing. But, you know, this would be, and this stuff is related usually to centrifugal chillers, because that's what you commonly see out there. So cooling tower, 3 GPM per ton, we've seen that. Design wet bulb, 78. That's what we still use probably in Cookeville, 77 or 78. Range, so the range is the amount that we cool the water. So the standard number was 95 in and 85 out, which is a 10-degree difference. So that's the range. And then there is some approach to wet bulb. So in this case, what? This would be what? This would be a 7-degree, right? Because here's my leaving water temperature, and there's my design wet bulb. So that would be a 7-degree approach. Okay? Getting the terminology down? Question? Some of these comments, I think, are somewhat dated, and I'll hand out some train engineers newsletters that address variable flow in chill water plants. So anyway, but this 2 GPM per ton, and that's on the condenser water side. People are starting to design systems for that down there. Technology has progressed a little bit, so we're starting to see some of this. He's making a case here that it's more energy efficient to go to 3, but I think a lot of time these days, if you take this down, approaching this, you can save that pump energy, and still the newer chillers can still provide the efficiency. So anyway, I'm not going to go through all of that in great depth and detail. Almost go through that. Things that do affect the performance of the tower, certainly airflow, how efficient is your fan, and how much pressure drop. And we'll talk about different types of fill. The fill is the media that's inside the tower. So the water comes in the top and falls down, through nozzles or holes into that fill, and it kind of breaks up, because you want to increase the surface area to promote evaporation is really what we're all about. And so there's different types of fill, and some of the newer fills are like, 3D printed kind of stuff and real complex plastic shapes that can be made cheaply. In the old days, this fill used to be some sort of exotic wood, like teak or something like that, and it was pretty expensive. Something that would not rot because it's sitting there wet all the time. I mean, every time, it's just got water constantly cascading over it with air blowing up on it. So in the old days, there was actually water. And after a while, some of it would rot. You come up in the fill, some would be broken down in one place, and ever so often you had to replace it. Well, these days that's all being replaced, and new towers come out with plastic kind of fills that are cheaper to make and operate much better, have lower pressure drops. So, water retention. Okay, let's think about it. What are ways that water can be lost from the condenser water flow at the cooling tower? Well, we mentioned evaporation. That's the whole purpose of the thing, is to evaporate water. So we got to have makeup water, right? What else? How else can we lose water at the tower? We've got this plume. We're blowing this plume of air. Either force draft the fans down here, and it's blowing high velocity in, and it kind of slows down, but we're still blowing a lot of air out the top. Induced draft, we got the fan up there, and it's sucking like crazy through the tower and then blowing up to the atmosphere. Well, droplets get entrained in that. It's called windage. So we're blowing droplets out of the top. Well, that's water that's gone. And it also we have to put chemicals in this condenser water. We have to constantly maintain the chemicals because, we're constantly adding oxygen. We're blowing it through the atmosphere and we're trying to promote evaporation. Well, that adds oxygen back to the water. That oxygen goes through the chiller. What happens? And in the piping, we get corrosion like crazy. So water treatment is very critical. And the other thing is, well, there's lots of other things. So when those droplets come out of there, they take chemical with them. Well, this is water. Can stuff grow in water? Like bad things? Like bacteria and all kinds of crud? Yeah, absolutely. Have y'all heard of Legionella's disease? You ever heard of that? Here, let's see if I can. Let's Google Legionella disease. I should have done this ahead of time. L-E-G. Legionnaires. Right there, comes up. Legionnaire's disease. Oh. Okay. Legionellosis, a form of atypical pneumonia caused by Legionella bacteria. This thing showed up in disease is named after the outbreak that was first identified at the 1976 American Legion Convention in Philadelphia, where they killed a bunch of people. There we go. Occurred in late summer in Philadelphia, the first occasion in which a cluster of particular type of pneumonia cases was determined caused by Legionella bacteria. So what happened is, this is the hotel they're staying in. And this hotel has a bunch of, like, through the wall, and it's pulling ventilation from outside the building. And there was a cooling tower very close by that was spewing out all of this contaminated water droplets. They got entrained in the air, and it got sucked up into the rooms of these poor retired soldiers at the American Legion Convention, and they breathed it. And I don't know how many, it probably says a bunch of them. 24 hours later, I was six more Legionnaires died. I mean, I don't know how many of them died. A bunch of them, probably says in there. But they had a bunch of these people get sick. 29 people died from breathing this stuff. Anybody want to go visit the cooling tower down here with me? We can crawl up on top and take a look at it. Well, I've been up there many times. I never had Legionella disease. But, you know, people now put biocides, and they put all kinds of chemical water treatment, not only to control oxygen, but to control the growth of crap that can get, you know, different bacteria and whatever that can grow in that water. Because that's, you know, 95, 85 degree water, man, those bacteria, man, they just grow like crazy in that stuff if you don't do something to stop it. So these days, if Tennessee Tech had an outbreak of this, what if one of you all died from this? You're walking, you know, you say you're living in Tech Village down there. You're walking down there every day, and you breathe this stuff, and suddenly you get sick, and they find you dead in your bed the next morning, and they trace it to this. You think your parents would want to sue Tennessee Tech for every daggum dime? You know, I mean, it would be a tragedy. And so there's tremendous liability now because this stuff is known. I mean, back in '76, you know, this hotel probably, or, you know, whoever owned the cooling tower that polluted it probably wasn't held too liable because nobody knew, right? This is the first time. But this day and time, and there was an outbreak a year or two. If you Google this further, up in New York, New York City, I was up in New York someplace. There was a number of people came down with this within the last year or two. So it's an ongoing situation. So you just need to be aware of it. So now you are. Let's go back. Okay. So in subsequent presentations, we'll go through some more of this. But anyway, so the way water can leave the tower, we have blowdown. Because see, all this evaporation, you have to have makeup water. Well, it's kind of like a boiler or something, you know. When you bring in that makeup water, it's a source of minerals and, you know, dissolved things that are in the water that we drink, okay? And so that will concentrate in the tower, and that will scale up on the tower. So they blow down water. They take water out of the sump, and they actually blow it to sewer so that you can make it up, because the concentration of that stuff will build and build and build. And the only way you can control it is to throw some out and put some more makeup water in, which has a little bit, but you're throwing away water that has a boatload of this stuff. And so you make it up with a water that has a very low concentration. And so you dilute what's in there to control it. So we've got blowdown, we've got evaporation, and we've got windage, basically, which is where the droplets come out the top. So we've got several different avenues that we can lose water from the cooling tower. And of course, these things are air washers. You see comments about dirt plugging and all that sort of thing. I mean, from the air perspective, you know, there's all kinds of dirt and stuff being carried along in the air, especially right now. I bet those cooling towers are getting pummeled down there with all this construction. Had a huge project at the new fitness center, and a huge project over here, and the cooling towers are right over there in close proximity to both of them. With all that dirt being pushed around in the air and all of that, I mean, that gets sucked right through that cooling tower, and that water just washes it right out. So I'll say those cooling towers have been cleaning up the air from that, taking particulates and stuff out of there. Well, that builds up. So I know every year they have to take those towers down, and you know, workers come in and have to shovel the crap out of the basins. You know, it builds up. Something else to consider. All right, let's move on. Looking at, you know, the physical condition, you know, make sure everything, you know, has not deteriorated, and all that stuff can have problems. Other considerations, and there's a lot in here. Just some pictures. Heat recovery on a chiller. So this is another way that we can recover energy. What you can do is, it's like having two condensers, right? So you have a standard condenser and you have a heat recovery condenser. So the hot refrigerant comes initially to the heat recovery condenser when it has the most temperature. And say you have a bunch of water that you're going to have to heat up. So maybe this is some kind of processed water. You know, for example, you know, what if you were making soup? You're an industry and you're trying to boil a bunch of soup. Well, you're constantly bringing in fresh water. You could run it through here and pick up certain degrees of heat, and that would be less heat you would have to put in from a costly energy source. So if you have a flow that you want to heat up, of course you have to buy an extra heat exchanger to do this, and then you have the standard condenser to make sure that all the refrigerant gets condensed. So that's a possibility. And this goes into a bunch of details right now that we're not ready to go into all this. Free cooling, there's different ways to do the cycles, but you have some kind of an idea. The one we talked about was the plate and frame heat exchanger over there. Some information on plate and frame heat exchangers. Okay. Looking at different ways to pipe this thing up. This is summer chiller operation. We're just doing this. This is your evaporator, that's your compressor. So you have 1,000-ton chiller, 300 GPM on the condenser water side, 2,400 GPM on the chill water side. So that's kind of standard operation. This shows a little more detail with some numbers on the a plate frame heat exchanger kind of a setup. What they've done here, so they've cut, interesting, they cut the flow rate in half in order to be able to get a better delta T, to get a 10-degree delta T across this plate and frame heat exchanger. And the hope then is that, say in the wintertime when you can do this, that you don't need as much chill water flow. So these things sometimes work well and sometimes not so much. Okay, that's pretty good. Free cooling, reduce chill water temperature change. let's see, so we're back to, well, we're back to 2400, so we're coming back at 60. So we're coming into the plate and frame, we're coming out at 55. Okay, and so this is showing us just going out at 55. So as we're looking at different, the ability to make different temperatures here. It's a similar situation. Free cooling, air preheat. So we have 100% outside air situation. Okay. So lots of types of buildings need to go on complete outside air. If you're doing maybe some manufacturing, research facilities that generate contaminants can't afford to return air. You know, you can't get all of the stuff out of it, chemicals or whatever. Okay. And so all of the air supplied by the heating cooling system has to be from the outside. Well, if it's cold outside, then, you know, this has to be heated up in some kind of a preheat coil before you go to the air handler where it gets heated up to the final discharge temperature. So this would show if we're running chilled water, we could put a plate and frame heat exchanger in, run 55-degree return water through one side of this, they drop it 5 degrees, and we can just run a loop around here where we can generate 50-degree water up here, preheat this air from 0 to 40. That will cool this down to 45 and just pump this around in a circle. And so this helps my cooling energy and this helps my heating energy. So I can move some energy from the chilled water into preheating the air. So that's an interesting idea. Let's see, condenser water heat recovery. So what are we doing? So we got a hot water system. Okay, and so we're taking the condenser water out of the chiller, going through a plate and frame, and so we can preheat over here, bring this in at 93, take it out at 108. And this one I think would come in at probably, let's see, we'd have to pick it up, so it'd be 110 here and 95. No, I'm sorry, 95 out of here and 110 out here. So anyway, you can do stuff like that. Filtration. Filtration's a big deal. All this stuff. Defense against Legionella. Removes food sores. Different types of filtration. Side stream, bag filters, cartridge filters, multimedia sand. So applications, cooling tower, side stream, sumps, processed water, air washers. I don't really have a lot of comment. Turpish is a filtration guy. He sells these filtration services and products. Different sweeper systems. I think I'm about done with this one. We got a few minutes. We're going to go on to the next. Filter sizing. Yeah. Okay. That's good. Okay, let me call up this next one here. Yeah. Okay. This is another intro. Some of this will be a little bit redundant, but there may be some stuff in here that we haven't talked about. So intro. So that's kind of a common picture. There's a few things on here, a little more in detail. Makeup water coming in. Need to meter this. The vast majority of the water that gets made up here is evaporate. In industrial, and I mean, it's even possible for Tennessee Tech. When you buy water from, say, the city of Cookeville, they also charge you a sewer fee. Okay, and the sewer fee is usually more than the water fee. So and unless you go to some trouble and set up an arrangement, they're going to assume that if you buy 100,000 gallons of water this month, you put it all down the sewer. They just make that, they're more than happy to make that assumption. And so when you look on your bill, you may have, let's say you have $10,000 water charge, you may have $12,000 or $13,000 sewer charge. And it's based on the amount of water that you purchase. But if you're running a bunch of cooling towers like this, these things in the summer evaporate a pretty good amount of water. I mean, if you're buying 100,000 gallons in the winter, you could be buying 150,000 gallons of water in the summer, and that water is being evaporated by the cooling tower. So you have to sit down, call them for a meeting, have negotiations, say, well, look, we got a flow meter here. We know how much water is going to that cooling tower. Now, the down and dirty secret is, well, we still have this blowdown over here. And, you know, if they're smart, they're going to say, well, you meter your blowdown flow, because that does go down their sewer. But most of the time, they're not sharp enough to pick up on that. And so you can talk about this flow. Well, this is the amount of water going to the cooling tower. That gets evaporated. It doesn't go down your sewer. You shouldn't be charging me sewer charges for that. And so you ought to be able to negotiate a credit on your sewer bill for water that goes to a cooling tower. Likewise, if this was going to a line that's making soup, and the soup leaves in the truck and goes to Kroger and Walmart and Publix and all these stores, you shouldn't have to pay sewer charges on that water either. So a lot of companies are on top of this, and a lot of companies are not quite sharp enough to pick up on it. This could be in the order of probably $5,000 to $30,000, $40,000 a year on a big operation. Mm-hmm. So it's one of those little tricks that you need to put in your toolbox when you think about purchasing water, you think about purchasing sewer, and then the question pops up, I wonder if all the water they purchase goes down the sewer, and that could be an opportunity for them. Okay, what else we have on here? So we're showing water with concentrated mineral salts, and that's because of the evaporation. We have some sort of a blowdown scheme by which this could be automatically controlled, or it could be done a couple times a day. We drain some water out of here, put in more to control that. We pump out of this basin. This is most likely a chiller, or it could be a heat exchanger, but that could be a condenser on a chiller. Warm water comes back in the top, somehow sprays out into the fill. We're showing drift up here. We've got some evaporation. So these are the three sources: drift, evaporation, and blowdown. And so that's pretty much it. Okay, components. Well, we've talked about different sorts of fill, splash, film, splash fill, and film fill, cold water basin. Drift eliminators. Okay, in the towers, someplace we'll have a picture of those. The picture's on further down. But what they do is up in here, they put what they call drift eliminators. And what they are is kind of a crinkled path that air has to go through, and it makes those water droplets hit a surface. So it's like at 45 degrees. Some of them are kind of like little stair steps on them, and that stuff hits it. And then those droplets hit, and they grab onto that, and then they fall back down in the tower. So that's what we talk about drift eliminators. Drift eliminators. Louvers equalize airflow, nozzles spray out, fans deliver. Okay, types, we've been through some of this. Natural draft, concrete. Okay, so let's see. So we actually have a couple of configurations here. One is a cross flow, and the other is a counter flow. There we go. So we have cross flow and counter flow also in these natural draft towers. So the water gets supplied down in here. I mean, it's not put up in here. This is all of this stuff. This tower is just to promote the airflow. So hot water distribution basin fill. So this is cross flow. So the air is drawn across this way. And then this one is jacked up a little bit. So the air comes in underneath it and rises further. Let's see. Okay. So I think we've been through this forced draft, induced draft, two types. It's probably some better pictures here. Let's see. Okay, so let's think about advantages and disadvantages. So FD tower, again, this fan is down here, blowing, forcing up across here. So what we see is that these fans are usually require greater horsepower because they're coming out of here at a high velocity and they're forcing that air up through the fill. They say it's relatively quiet because the fan is somewhat closed by the tower itself. Recirculation, because what happens is, here's my drift eliminators up here. By the time I get to the top of the tower, the velocity is not so great compared to the induced. The induced draft, the fan is up here and it's blasting up the top. So you get much greater velocity. This one, the higher velocity is down here at the bottom where we're sucking air like crazy into this centrifugal fan. And up here, the velocity is much less than the induced draft. And so that gives us a greater opportunity to pull some of this back around in here. So the forced draft fan, recirculation due to high air entry and low exit velocities. So that's probably the main. I would say that, and the fact that for a given tower capacity, I think the horsepower rating is typically larger on the FD fans. So energy and recirculation. Reduced draft. So we've talked about that. Advantages, less recirculation on the induced draft. Yeah, and the disadvantage here is that in the induced draft, these fans are right up there and all of that moisture, that air is 100% saturated and all those droplets are up there. So it's a very wet environment. So that's going to lead to more maintenance issues. Nothing's perfect. Induced draft, counterflow. Here's the bottom, the top. Yeah. I don't know that there's much there. Maybe it's a little bit better pictures. Let's see. Induced draft, counterflow. And water down there. Oh, this is showing without fill. I don't think there's many of these. I've not seen much of this. I mean, this would just be a spray chamber. I guess they've made some. I've not seen. I don't know if I've ever seen one of these things. But anyway, that would just be a header, spray nozzles, and then the air turning, going up through there. Most likely you're going to have some kind of fill that just comes down and spread out. Induced draft. Yeah, cross flow. Most of them are double like this, where you have fill on both sides. Some of the smaller ones can be set up that way. These distribution chambers up here maintain a certain depth of water. These nozzles, basically they're just holes cut in this line with metal. And so they require a certain depth of water in order to get the right distribution. So if you run too much, you can overflow this, and if you run not enough, you won't have enough pressure, and you won't get good wetting on all of the fill. That's about it on that. Assessment of cooling towers. So all of the parameters that we can measure to assess the operation of a tower, probably the most important, and that's why it's first, is the wet bulb temperature of air coming in, because that's what really defines your potential for cooling. Dry bulb temperature certainly has some impact. I mean, there is some convection and radiation and all of that, but it's by far a secondary mechanism. The inlet outlet water temperatures, exhaust air temperature, the electrical readings on the fan and the pump, and the water and airflow rates. So that's a fair amount of stuff to measure if you want to really do a complete evaluation on one. I don't know. I just put it in there just because, you got to have a site chart around. We've already kind of talked about that. Okay. Let's go through. These are the performance parameters. So I've talked through this, but this is probably a better way to present it. So difference between the cooling water inlet and the outlet temperature. So hot water temperature in, cold water temperature out. That difference is range. Wet bulb temperature here, and that difference between the cold water temperature and the wet bulb in the ambient is the approach. So we pretty well seen that. Okay, effectiveness in percent. The range divided by the range plus the approach. So whatever you're getting here divided by this distance here, expressed as a percent. Yeah, so I mean, if you had a tower of infinite size, but this is going to go all the way down here, and this is going to be 100%. Cooling capacity. Okay, heat rejected in BTUs per hour or tons of refrigeration, while m.dot CP delta T, or in US units, there's a handy approximation, which is pretty good. I'll write this up here. This is one that's worth remembering. For standard water, that Q dot is equal to 500 GPM times delta T. Standard water, which is, anything, you get above 150 or something. Because I mean, that's standard density and all of that is specific heat is in the 500, but it's pretty easy to remember 500 GPM delta T. That'll work just fine on a cooling tower because we got water, certainly less than, not much more than 100 max, and leaving. It's much cooler than that. So, and this is, this gives BTUs per hour. Okay. So, I mean, you don't have to, but sometimes it's handy to have some of those things tucked away. Okay. Evaporation loss, some other standard ways of calculating here. Theoretically, oh my goodness, somehow we got meters cubed and kilocalories up here. So you guys will be happy for that. So water quantity, meters cubed per hour, evaporated for cooling only. Theoretically, 1.8 meters cubed for every million kilocal of heat rejected. So we can write a little equation to calculate the amount of evaporation loss from the tower based on the circulation rate, meters cubed per hour, and the temperature difference. So, cycles of concentration. That's actually 1 over the blowdown rate. Evaporation loss divided by the cycle of concentration minus 1. So this is how cooling tower people talk about their blowdown rate. It's a ratio of dissolved solids in circulating water to dissolved solids in makeup water. So see cycles of concentration discussed. Okay, I think I'm going to pull up there, and we will continue on Tuesday. So work on those homeworks, and let's pick those up on Tuesday.